Alright, welcome back. So in this lesson we're going to talk about mass energy equivalence in terms of nuclear reactions. If you didn't watch the previous lesson when we were talking about energy mass equivalence, the importance of it, what does it do in terms of combustion reactions and antiparticle annihilation, I do encourage you to watch that first. But we're going to go through this with nuclear reactions now. So before we start, let me just talk about what is a nuclear reaction. Okay, there's two types of nuclear reactions, but everything has to do with inside the atom. So we know that with the atom, okay, we know the basic structure of the atom is you have your neutron, or you have your nucleus at the center. You have the proton, you have the neutron, and then you have the electron outside. What we're talking about with nuclear fusion reaction or nuclear fission, it's everything to do with inside the nucleus. So hence why obviously it's called a nuclear reaction. It's a reaction of the nucleus. Okay? And if we're talking about nuclear fission, we're talking about the nucleus of the isotope breaking itself apart into smaller products. If it's fusion, the nucleuses are adding itself together. Now, I did use a term just then called isotopes. So for those who aren't familiar or need a bit of refreshing what an isotope is, it's the same element, meaning it's the same type of atom, so it has the same number of protons, but they have a different number of neutrons. So here we have the diagram showing you three different types of hydrogens, all isotopes of each other, obviously. You can see there's only one proton there, but one's called hydrogen 1, one's called hydrogen 2, the other one's called hydrogen 3. Now, the way we denote these numbers is we call it its mass number. So the relative mass that's inside this nucleus. So a proton has a relative mass of 1, so does a neutron, roughly about that. So we have a proton and a neutron. We have a mass number of 2. If we have one proton and 2 neutrons, we have a relative mass number of 3. So that's where we're going here. All right, now before we start, let's kind of look at in nuclear reactors, fission. So what we actually know is with nuclear reactions, they'll have the fuel source, and it's going to cause a massive release of energy. That energy in the form of heat is used to heat up water, and that water is used to turn these turbines. And if you recall from module 6, these turbines are made out of the connection of really strong electromagnets and wires, and that's the creation and production of electricity. Now, nuclear fission reaction, and this kind of happens in all of them, what's actually happening is when you fire a really slow moving neutron, when it collides with the uranium nucleus, it breaks itself apart into multiple parts, and as it breaks itself apart, it's releasing an enormous amount of energy. But what we do realize is when this when the nucleus breaks itself apart and we try and count the mass individually, there is a slight change in the overall mass. So if you have a look here, the unit U just stands for atomic mass unit, so the relative mass. It's 4.0026. If I then count the things that were released from this breakage, the mass has actually gone up. Okay, so that's what we mean by a mass defect, a change in the mass from the initial to final products. Okay, and this is where the beauty of equals mc squared comes in, because we can actually work out this mass loss is converted into energy, vice versa, energy is being released at some point either way. So what we mean by mass defect is the loss in mass when atoms mass is compared, or the nucleus of the atom, its mass is compared to the individual protons and neutrons inside of it, or we just mean a difference in mass after a nuclear reaction. Now, the energy that's released is known as its binding energy, but it also refers to the minimum amount of energy to hold the nucleus together. When you break the nucleus apart, that breakage will release binding energy. When you fuse them together, some of that binding energy that's not used up in holding everything together is released. All of this can be calculated using E equals mc squared. If you actually have a look at the trend of the binding energy for each specific type of element, you'll see that it reaches its maximum point for iron, and then it just progressively gets smaller for larger nucleuses. Now, the overall binding energy is still very high, but per nucleon, which is the actual nucleus, gets a bit small. The reason being is we know that as it gets bigger, the forces in holding the nucleus together becomes a lot more difficult because there's all these repulsions between the protons. That's going on there. If we look at the formula to calculate mass defect and binding energy, mass defect, we're going to denote it as delta M, and we are going to use absolute value. So it actually doesn't really matter which one comes first, initial or final, but you're going to subtract the two from each other, and you're going to absolute value them to give it a positive value, obviously because it's positive mass. And then once you're done, once you've found the mass defect, you're going to apply it into Einstein's formula E equals mc squared. That's going to help you work out the overall energy that was released into the surroundings. So if mass defect was calculated in atomic mass units, so MAU, or in the diagram I showed you, lowercase u, instead of representing this as joules, you're going to represent this as mega electron volts. Okay, so 1 mega electron volt is the charge of an electron times 10 to the power 6. Obviously, if you can't remember that, you can just times the charge of an electron into your value for joules, and that will convert it into electron volts. Okay? Equals mc squared if you're going to get it in joules, you're using kilograms. Equals mc squared if you're getting it in electron volts, you're using atomic mass units. So let's have a look. Let's give this a go. I'm going to try and calculate the mass defect of a regular carbon atom that has 6 protons, 6 neutrons, and compare it to the overall mass that the actual nucleus will have. So we're going to calculate the individual parts together and then subtract that from the original mass. Okay, so I know that for the mass of the 6 protons and the 6 neutrons, it's 6 times the value of the electron, or the mass value of the electron, plus 6 times the mass of the neutron. Okay, so there's that one there. Now, I'm going to also subtract it by the total mass of the nucleus, okay, and that will give me a nice little value there. So, I'm going to do this, I'm going to make this into delta M to show the mass defect. I'm going to subtract that by the overall mass of the nucleus. So, again, we're actually measuring 6 protons and 6 neutrons, but one is their individual mass, the other is the mass inside the nucleus. And we get a mass defect of 1.58 times 10 to the power 28 kilograms. Okay, it's a very small difference, but a difference nonetheless. The total binding energy, if we substitute that value in, we'll find that the binding energy is 1.42 10 times to the power of negative 11 joules. So that's how much energy was released when we release these 6 protons and neutrons out of its nucleus of carbon. Okay? Another scenario you might get is trying to read isotope equations. So like I said before, the top number will tell you the mass number. That's just how many protons and neutrons you have. And the bottom number is called the atomic number. That will tell you the number of protons you have in total. So you can kind of work it either way. You can actually use the atomic number to work out the number of neutrons. So it'll be 14 minus 6. So this carbon 14, has 8 neutrons. So I'm going to try and work out the total mass defect and the energy that's being released in this example here, and then we can go from there. Okay, so if I have a look at the table here, beryllium has a mass of 9.0122 plus the mass of helium. Subtract that by the mass of carbon, 119967, and also subtract that by the mass of the neutron. Okay, so the mass defect I have here, and obviously I'm just basing it off this table, so you do that as well. The total mass defect is 0.0094 atomic mass unit. Okay, if I want to find the binding energy difference, energy released, it is atomic mass unit. So energy is atomic mass unit so times the value constant that we had here, 931.5. This is actually c squared, but we've converted that c squared into the value of electron volts, and we get 8.756 mega electron volts. So that's the answer there. You can use this same strategy to go through the second question as well. Okay, the other type of nuclear reaction we're going to go through is called nuclear fusion. Okay, so nuclear fission, the one that we talked about just then, is when you break the nucleus apart into smaller components. Nuclear fusion, though, is when you have two small nucleons or nucleuses and you combine them together. And this is essentially how stars work. So I'm going to use the example of our sun. The sun actually goes through multiple nuclear fusion reactions that we'll also talk about in Module 8. So the very first one we get is the hydrogen plus hydrogen to make hydrogen 2, makes a positron, and it also releases a neutrino. Okay, so there's that. Once that's formed, this hydrogen 2 plays its role as well. It will then form a nuclear fusion reaction with another hydrogen 1 nucleus to form helium 3. That helium 3 is going to combine with another helium 3 to make helium 4, another hydrogen, another hydrogen. Obviously these two can then go back and start with that. So what we talked about before, it kind of explains to us why the sun has a continuous amount of hydrogen to a certain extent. That's why it doesn't really run out of hydrogen that quickly, because it's after this nuclear reaction, it's continuously building and producing more hydrogen atoms or nucleuses. Okay, so this is actually the percentage of all the different types of chemicals in our sun. It's about 99% hydrogen and helium only, with a really small amount of all the other elements. If we try and do the calculation here, we want to work out the energy mass equivalence. We will also look at the temperature and fusion of helium here. So I'm just going to go on ahead and show you the actual calculations done. So the final mass minus the initial, again, like I said, doesn't really matter which way you do it. Absolute value them, you get your positive value. The mass defect inside the star when 4 protons are forced together into an alpha particle, that's the amount of mass defect that we'll see, 4.41, 10 to the power minus 29. The overall binding energy we get equals mc squared. That will give us a value of 3.98, 10 to the power of negative 12. So that's the amount of energy that's being produced as we go along inside the sun when it's fusing all those protons together. So the last thing I want to kind of show you is how do we know how long our sun can live for? So if we have a look, so during the process of nuclear fusion, the sun experiences a mass loss of approximately 4.4 trillion grams, or 4.4 10 to the power of 9 kilograms. That should be in kilograms, probably, per second. So that's a lot of mass being lost, okay? Now our sun has a mass of 2 times 10 to the power 30, 10 to the 30. So it has a lot of mass to use. And remember, as it's going through this, the whole function of the sun is the fusion reaction between the 2 hydrogen atoms, or 2 hydrogen nuclei, that generate all this energy. So the sun has a massive amount of mass. It's giving off a decent amount of mass loss, but that's kind of how we kind of predict how many years that's left on the sun. That's how we do our predictions. Okay? So that kind of rounds off this part of the section, which kind of covers through how mass energy equivalence is used with the production of energy from the sun. We know that the sun will lose some kind of mass, and that mass loss inside of the sun will create energy. That energy will come in the form of various types. It can be gamma radiation, UV, infrared radiation, all those of the electromagnetic spectra, and that's what we get. You can also have a look at some other parts of these questions. There's plenty of these calculations that you can pause and try and do yourself, but the ideas will be very much the same as the explanations we did beforehand. Alright, so that concludes this part of the inquiry question, and it actually ends the entire module 7. So we started from module 7, we talked about light, what is light, wave, particle, we've talked about it in terms of special relativity. We've also linked how mass and energy are the same thing, or can be interconvertible, and we've also shown the idea of special relativity. Alright, so that kind of concludes everything. If you want to just go back and revise on all the different things, remember, have a look at the playlist on the screen, and also don't forget to have a look at some other videos to refresh your understanding of these physics concepts. Either way, I'll see you again in module 8. Have a good one.